Hi, this is the video for section 3.3 of A Student's Guide to the Schrödinger Equation. This one's about the time-independent Schrödinger equation. To get to the time-independent form, you can use a technique called separation of variables that you may have run into in a physics or math class. And as it says in this introductory paragraph, this technique relies on being able to write the function you're trying to solve for, in this case psi of x and t, as the product of two functions, one depending only on the space variable x and the other depending only on the time variable t. As it says up here, there's no a priori reason why this has to work in every case, but it often does work, and in quantum mechanics it is an extremely powerful technique. To see how that works, simply substitute this expression into the Schrödinger equation wherever you see a psi of x and t. And the reason this is powerful is because these are partial derivatives. That means that in this case, the psi of x can be brought right out of the derivative, and in this case, the t of t can be brought out. And when you do that, those terms look like this. Then, if you divide through by psi of x times t of t, you'll notice what happens. Some of these terms cancel, and you're left with this equation. And this is extremely powerful. As long as the potential energy V depends only on space, that is only on x and not on time, then this whole side of the equation depends only on x. And this whole side of the equation depends only on t. The reason that's so powerful is because if the left half depends only on t and the right half depends only on x, then both sides must be constant. There's a little explanatory paragraph here about why that's true, and it says, just think about what would happen if this side wasn't constant and changed over time. Well, since this side doesn't depend on time, it wouldn't be changing, while the left side would, and the equation wouldn't hold. Likewise, if the right side were to change over space and the left side depends only on time, then if we move position, the right side would change and the left side wouldn't. So that means that neither the left side nor the right side can change. And if they can't change, they must both be constant. As it says down here, some students find that a little bit troubling. After all, we know that psi is a function of space and time, so how can these be constant? Remember, we're not saying psi is constant. Psi is definitely not constant in virtually every interesting situation in quantum mechanics. But what is constant is that entire left side of the equation and the entire right side of the equation. That's very different from saying that psi must be constant. So what does it mean if these sides are constant? Well, let's look at the left side first. Here we've written the left side just as a constant called constant, and if we do a little algebra and integrate both sides, you come to this equation, which says the function of time, t of t, is simply an exponential with e to the negative I times the constant over h bar times time. We're going to call that constant e. As it says in a footnote down here, you can actually see it must have dimensions of energy, but for now, we're just going to call it e, and that makes the time function t of t look like this. We'll come back to that, but for now, look at the other side of the equation. It's also got to equal e, because after all, the left side of the equation equals the right side, and we set the left side to e, so the right side must also be e. Again, if we multiply through by psi, we come to this expression, and this is called the time-independent Schrödinger equation. In many, many quantum mechanics problems, you're going to solve this equation and then marry those solutions for psi of x with the solutions for t of t to make psi of x and t. But before we see examples of that, look at what you've got on the left side here. We said that's the Hamiltonian operator h, and if that's h, we can write our equation as h psi is equal to the constant e psi. But you know what kind of equation this is. That's an eigenfunction or an eigenvalue equation, in which psi of x is the eigenfunction and e is the eigenvalue. So that's why you'll see some people describe solving the time-independent Schrödinger equation as finding the eigenvalues and eigenfunctions of the Hamiltonian operator. One other point is that you're likely to see the terminology stationary states applied to the functions psi of x. Some people think that might mean that psi of x and t is somehow not changing or stationary over time. That's not what it means. Stationary states simply mean quantities such as the probability density or expectation values. Those do not vary over time. And you can see why that's true if you form the inner product of psi with itself. We know how to do that. We're going to take psi star psi, and when I take the complex conjugate of this side, here we've plugged in what that time term looks like, and notice that this complex conjugate means that minus sign becomes a plus. So here you get an e to the IE over h bar, and here you get an e to the minus IE over h bar. Those two terms, when you multiply them together, cancel, and you're left with simply psi of x star psi of x. So the time dependence has disappeared whenever we can write the function psi of x and t as the product of psi of x and t of t. That's what stationary states mean, because things like the probability density are going to depend on this quantity, and there is no time dependence there. So, since the time-independent Schrödinger equation is an eigenvalue equation, lots of the formalism that we talked about in Chapter 2 can be applied to the solutions to the Schrödinger equation. You'll see some of that in later chapters, but before you get to that, the next section is about the three-dimensional version of the Schrödinger equation. That's it for this section.